Here is where we left off in the last video. It's a kind of recipe for building an extended Kalman filter when your uh, underlying system model is continuous time and has nonlinear dynamics, potentially a nonlinear relationship between your measurements and your state vector. We kind of, I'll say, derived it, even though we just made several approximations, all based on tailored series approximations to replace nonlinear functions with linear functions out some operating point. And that operating point is our estimate of the state itself. Anyway, that's how we got here. Some of these are calculations you will do ahead of time, all to end up putting it in a computer program, an algorithm. So some of these things are done by the computer, and some of these things are computed ahead of time to know what to put in the computer. Like taking these partials, you do that ahead of time. Finding phi, you'll do that ahead of time. So there's a bunch of things we need to compute. So let's do an example. Ballistic vehicle tracking in one dimension. All we track is the vertical position. Y is the vertical position. Y dot is its vertical velocity. Y double dot, its acceleration. Gravity will pull it down, but drag will push against that. It'll push it up, proportional to the velocity squared. So we're already nonlinear right there. And this rho, the sort of drag coefficient or air density factor, is going to depend on your altitude. So that's another nonlinear relationship. And we'll say we measure it at uniform time steps, and our measurement error is, we'll assume, zero mean with known variance. So the measurement model is nonlinear. We just measure y directly. So we have to come up with what are all these matrices? Because these are the things you either calculate or you program into a computer. First, what is the F, the little f? It captures the nonlinear dynamics. This U sub D, by the way, was some non-random known input. In this case, it will be gravity. There's our known input. But here's our little f. In terms, well, not quite. This is a second order equation, so we'll use state space. We'll say x1, the x1 state variable is y itself. x2 is its velocity. So x1 dot, x2 dot is y double dot, which is this mess where I plug in this row up here, which is all that. In terms of my state variables, then, it's this. And now I can put it in a kind of state space form. Here's my little f. It's a vector of nonlinear functions. Well, this one happens to be linear. This one is nonlinear. I'm going to tack this on right now as a kind of placeholder, but I'm going to talk about it later. In effect, we added some unknown white noise to this acceleration. I'll tell you why in the next video. So we have to find all these things. Here we just found F. Here it is. H, we just measure Y, is this 1, 0 matrix. And R then is just the whatever our measurement variance is. And this is just a scalar variance. Now we got to go on and find these other guys. Well, G is this little matrix here. It's this thing I added on, and we'll talk about it later. So we need to come up with this capital F, V, and Q. I think that's what we haven't done yet. I mean, big F and phi. This vector equals the F. That's those two functions, which was this in our case. How do you find capital F? You take this first matrix of first partials. It means this, all evaluated at our current estimate. For our particular little f's, F1 and F2, it's this. And when you take those derivatives, you get this. This is our capital F. I'm going to just call, so I don't have to keep writing all this notation all the time. I'm going to call this guy here F21 and this guy here F22. The calculations you make, their results will be constants at a particular time step. Make these calculations based on your current estimate of the step. Then your phi is calculated from that. This was a result of a truncated matrix exponential. We talked about that. So in our case, this, and for the phi at this particular time step, you just replace all these taus with the actual time step, capital T, seconds, whatever it is. All evaluated at your current estimate. And what is Q? Just like in the Kalman filter, it's this, but in a way, it's easier to evaluate. I won't go through the matrix arithmetic. It's matrix multiplication. It's this. You end up with this, but you're integrating over tau, and tau only shows up as tau or tau squared. So the integration of it is easy. You integrate from 0 to capital T, you get this. All multiplied by that thing I haven't explained yet. Why did we even put this in here? But if you call this thing 0, which you might have thought we should have done, that means no measurement error at all, no process error at all. And your Q matrix for your Kalman filter would be 0. We kind of don't like 0 Q matrices, and I'll talk about that later. So anyway, here's the result. At prediction, you got to calculate those little F1 and F22 terms, which are these easy enough. Evaluated at your current estimate. Then from that, you can construct your phi matrix. Then from that, come up with your prediction of your state vector to the next time step. This means multiplied by the time step. And you can calculate your estimation error to the next variance of it, covariance of it. And then once you get to that next time step, in this case, it's like all the same calculations as the Kalman filter. The normal extended Kalman filter, this would be a little non-linear term here. But in this case, the measurement equation is already linear. So this looks all like a Kalman. So that's going through the process. Next, I'll leave it for another video to see what are the results and talk more about this. Save that for another video.